there's a bunch of errors that can come up with this, and I'll be very honest, maybe you guys are going to have, with our instrument, the data acquisition board tends to throw errors every once in a while irreproducibly. And you know, it's a real shame too when it happens in an important experiment at 10 at night when no one's here. For that reason, I think it's extremely important to not walk away, at least until you're beginning to collect data and you like what you're seeing. That's why I'm doing this manual first set of scans, so that we can test that things look right, that everything's behaving right. Then we will set up the run and hope that, you know, things don't, you know, particularly for new instruments or something. As I say, the machines that I use in our lab, one of them actually was a prototype that was donated to the facility when they were first building these. So, you know, they've really seen a lot of use. Good. And that's cell 1. And it looks excellent, I will say. Surprisingly good. No, I'm just joking. So what I'm saying about it is that you can see the sample and reference. This is the reference meniscus. This is the sample meniscus. We loaded a little bit less. And we wanted an OD. I think originally I thought the OD was 1, but then you mentioned it was about 1.4 or something. And so when you multiply that by the 1.2 centimeters, we should end up with an OD that's around 1.8, which is what we're probably about 1.4. It's actually it's a little bit less. It's in about the right range. This sample 4, I see something else that's happened at rotor speed. This one, the absorption is right, but we had something happen which I was a little bit worried about. It looks like the channel between the reference and the sample has leaked together. So it's mixed. I looked and I noticed, I don't remember which of the cells, but on one of them I could see there was like a bit of dirt that had been caught in the windows when they were put together, and that can act as a channel. So you can see now the sample and reference now are 1. That is not a huge problem. It might still be analyzable, okay. And that's one of the reasons when we assemble cells, I was mentioning, one of the things we do is we have like a compressed gas cylinder, or else like a little can of like, you know, which you can get to blow off. And you want them to get all the dust off the windows and the centerpieces before you assemble them together, because that can cause a leak between the two. This one looks fine. It's got the right, and again, it's loaded a little bit less in both channels, but the difference between them is what we would have expected. The absorbance on this one is around 0.2, which is about what we would have thought. Again, I'm just ballparking it. There's a 10-fold range that we set up between these cells. So so it's the middle cell that looks like it had a little channel leak. But you know, we can try to analyze it, and even if it's a problem, then we can still live with it. The thing I'm a little concerned is this one moved a little bit to the right. I hope that this one isn't leaking as well. It could be. We'll only find that out as we run additional sequential scans. The other thing that we can do is to just see if this is a slow leak or not. And honestly, I mean, the thing this points to the importance of assembling. You know, clean, and you get much more leaks with velocity than you do with equilibrium. That's maybe one of the downsides. But certainly there's no catastrophes. There's not, and what I'm ready to do now is to change this option to stop it after the last run. And now we're going to start the method scan. And the only thing that I don't need to do another radial calibration because we just did one. And it will now tell you that we're going to be scanning, doing a total of 240 scans. That makes sense because we're doing 80 scans times 3 of each cell. And it should basically start scanning every cell and never stop. I mean, it's just going to continuously go. And maybe something I'll do is when it shifts, it's just going to go through cell 1, 4, and 5. When it shifts over to the next cell, I'm going to start my clock and just see how long it actually takes. It's probably, as I say, it should probably be about a minute and a half. You can see already this is the boundaries. It's already now gotten cleared. The meniscus is almost at a 0 absorbance. So this is sedimenting pretty well. One thing that we like to also do, I don't know, is I'll do that later. These things are too big. You may want to change the resolution on this monitor to make it so you can fit things in there better. Just see. So now I can see when it gets to the second scan. Actually, your instrument is faster than my instrument. That took just over a minute. So, in fact, it's good that I threw on a bunch of scans at the end. That's actually great. So you get about a minute with these parameters. One thing I really don't like, and this software was written in a format that it runs under this origin software, this plotting routines. There's no way to change the scale on this real-time output. It would be very nice to have a way to arrange these so we could put, nicely arrange each of the cells and watch them with the scale that we want to look at it at. It automatically auto scales all of them. So that's the problem here. You see, you can barely see what's going on. And yeah, that's a problem. We just don't have enough room to conveniently display everything. I like to set it up, to tile it, yeah, so you can see all the scans as they're running. So, as I say, it looks like this one is perfect. Oh, look how quickly. So, yeah. So, this is going to happen real fast. We could, not at this point, you're sort of committed. But that's actually really beautiful. It's very nice because you get an impression in real time. It's actually sedimenting considerably faster than we would have expected for the dimer, and I guess you thought it might be more incredible. Maybe at the lower concentration.